All right. Okay. So, did anyone have any questions from section 4.1, which is due this evening, that they wanted me to go over? Okay. Shayna, did you have anything? Okay. All right. Then the only thing we have for today, well, I shouldn't say the only things we have for today are to, let's see, there we go, are to do some applications on the natural logarithm and some graphs. So that's what we're going to be working on. Let's see. There we go. I'm assuming you all can see me writing. Natural exponential, sorry. Not logarithms. Logarithms are coming. All right, natural exponential. So we're going to start out by looking at the graph of f of x is equal to e to the x. All right. Now, note, this is just like f of x is equal to a to the x, in that we still have a base function and a base of e. Do you remember how much e is worth? There you go. About 2.718. Yep, y'all got there. Okay. So it's the same as this function, except our a is this value e, which is about 2.718. This gives us the same 3 base points, in that you would have a negative 1 over e, 0 would be a 1, and you'd have a 1 e. Those would be the same for any exponential function. Your a would be different, clearly, but other than that, it would work out the same. Where is that? That means that I can graph this by using 1 over e, or e to the negative 1. Either one of those would work. Second e. Oh, can we not see because I'm too bright? There we go. E to the negative 1, which is about a third, 0.36, or 1/3. So I'm going to have a negative 1, about 1/3, 0, 1, and then 1, 2.7, or just below a 3. This is my graph of e to the x. Yep. Oh, stop trying to get a hold of me, people. Teach it. Okay, now we want to use the same types of transformations as we have done before. So let's try a couple of transformations on this. If g of x is equal to a negative e to the x, what does this negative do in front of that e to the x? Not over the y-axis. This is a reflection over, yep, that's going to reflect it over the x-axis. So I can take those same 3 points, and instead of -1, +1/3, it's going to be -1, -1/3. Instead of 0, +1, it's going to be 0, -1. And instead of a 1 and then just below 3, it's going to be just above -3. This is what happens for a negative e to the x. What happens if I put the negative not in front of the e but on the x? No. No. Doesn't expand it, and it's not going to shift it. At least I don't think that's what you mean by shift it. This negative reflected it over the x-axis. This negative is going to reflect it over the, there you go. So when you put a negative on the exponent, it goes from growth to decay. We talked about that the last couple of days. But when you put the negative on the exponent, it flips it from one of growth to one of decay, or from one of decay to one of growth. So that means instead of a -1 1/3, it's going to be a +1 1/3. It's still got to go through 0, 1, and it's going to be -1 that's just below the 3. And there's my e to the negative x. What happens if you add 2 to the function? Ooh, no. Up to, yep. This would shift it up to, we'll make this one purple. So all of these points would just get shifted up to. So instead of 0, 1, it's going to be 0, 3. Instead of 1, 2.718, it's going to be 1, 4.718. And instead of a -1 1/3, it's going to be a -1 2 1/3. Note that this also shifts your asymptote. When I keep the -3 in the exponent, what does that transformation do? Because I'm acting upon the x, it does the opposite of my intention. So, or the opposite of what it looks. So since it looks like we might go to the left 3, we're actually going to shift it to the right 3. So that means that a -1 1/3 will now be at 2 1/3. 0 1 will now be at 3 1. And 1 2.718 will now be at 4 2.718. Uh-oh. Hold on 1 second. I'll be right back. Sorry, I almost blew up my coffee pot. That would not have been a good thing in a quarantine to blow up my coffee pot. Okay. All right. I haven't done all of them, but I wanted to do this to sort of jog your memory about the different transformations, because that is something that we're going to be working on here in a second. Do you have any questions about the different transformations? No, Shayna, you good? Okay. And Ben, you're still all right? Okay. All right, so let's try. Where's it? There it is. Boom. All right. All right. So here's 2 examples of some of what you'll have to do. We're going to graph these functions using transformations. Oh, shoot. I don't have. There we go. And then my second example, I'm going to let g of x equal, oh, shoot. There we go. I don't know. 4. Okay. All right. So here's my graph, my XY graph. Remember our base function is going to be e to the x. That should give us 3 points to start. The -1 with 1 over e, 0, 1, which is in all of our different exponential functions, and 1e. I like to take a pencil and graph these 3 points to start. So -1 and about a 1/3, 0, 1, and a 1, 2.78. This is going to be my original function, or base function, of e to the x. Now, using our transformations, we need to decide what is that negative going to do and what is that -3 going to do. One at a time, working from the function out. So the first thing we want to do is decide what is that negative going to do. Okay, so we're going to need to reflect over the y. That'll take care of that negative. And then this -3 is going to, what's that going to do to our graph? So that's going to then drop our y values down 3 units. So now I'm just going to take one of my markers. I like my pink one here. And I'm going to start with this point first. I'm going to flip it over the y and drop it down 3. 1, 2, 3. For 0, 1, I'm going to reflect it. Nothing happens because it's already on the y-axis. And drop it 3 points. Then 1, 2.718. Reflect it over the y-axis and drop it 3 points, or 3 units. Notice that your horizontal asymptote has also been shifted. Since our horizontal asymptote would have been at 0 originally when we dropped the graph down 3 units, our new horizontal asymptote is at y equal -3. Questions? Good. Let's try our second one here. Here we have g of x is equal to 2x, e to the 2x plus 1. Our base function is still e to the x. Giving me the 3 points, -1, 1 over e, 1, 0, and 1e. Here's my base function e to the x, looking something like that. Now, working from the inside of the function out, what is this 2 going to do to my x values? Um, it looks like it should stretch it, but remember from transformations, when you're affecting the x, it actually does the opposite. It's not it's not going to stretch it. It's going to, well, we call it compress, right? It's not a stretch, it's a compress. Shrink usually goes like that. It's just a weird thing. So this is going to compress x by half. And that plus 1 is going to raise it up 1. So what does that mean for the points? That means all of my x values. Oh, shoot. I've got this one written wrong. You guys need to call me out on that. Okay. It means all my x values are going to be cut in half. Looks like they're going to be doubled, but they're actually going to be cut in half. So instead of negative 1/3, it's going to be a negative half 1/3, and then I need to raise it up 1. Instead of 0, 1, it's now going to be 0, 2. And instead of 1, 2.78, it's now going to be 1/2, 2.78. Oh, 3 points. I gotta go up 1. My bad. There we go. Plus 1. All right, hold on. Oh, did it stop sharing? Huh. How's that? Are we back? Okay, thank you. Okay. All right, but do you see how that took those and like squished them together? Compressed it a little bit so it climbs a little bit faster and it falls to 0 a little bit faster. That's the idea when it comes to those guys. All right, questions for me on those? Any other ones you might want to try? Nope, nope. Okay, so for this particular, right, we know that e to the first is the 2.718. Yes? But if I have e to the 2x, then if x is 1/2, that's when I get e to the first. So that means my e to the first actually has to move into the 1/2. Because I'm doubling the 1/2 to get the 1. No, I'm not doubling the 2.718 at all. It's exponential growth, so it doesn't work that way. My x value needs to be half as much to get to the y, because my x value is always going to get doubled here in the expression. So in order to get to an e to the first, or a 2.78, I only need that x to be 1/2. To get to an e squared, I only need that x to be 1. Okay, so I'm actually climbing a lot faster, so it compresses the graph. Okay? It's hard to say it the right way. Different people understand it in a slightly different manner. It's just a weird kind of thing. Okay, a couple of applications maybe. Okay, let's see. All right, so I won't be able to do all of the applications for you. There are several in your homework, but I did want to go over a couple of things and one formula, 2 different examples. So the first thing I want to talk about is continuous compounding. We've talked yesterday about the compounding interest formula, where you have A is equal to P 1 plus R over N to the NT for compounded interest. This formula is used when the compounding periods are finite. That is, they're a definite or finite number when there are 2 compounding periods a year, known as semi-annually. Or if they say it's compounded monthly, or if they say it's compounded daily. All of these are definite numbers that you can give me, right? A 2, a 12, a 365. For continuous compounding, we use the natural exponential function e. Continuous compounding is used when basically you don't even take a breath to figure out what an answer is, to put it back in to start all over again. So continuous compounding is growth that never stops, there's no definite periods. It's just always being calculated. The meanings here are the same. P is your principal, or the amount invested. R is your interest rate as a decimal. And T is your time in years. This formula is used for continuous compounding. If you do not see the words continuous compounding, you can assume compounded interest here. All right. So to tell the difference, so Mark has a choice between a 2.25% interest compounded monthly and 2.2% interest compounded continuously. Which will give them a better return. Now, the 2.25% does have higher interest. This is a higher interest rate. So it may seem that this is automatically going to be better than 2.2. However, the more often you compound, the better your interest return is. So while this one is only going to be compounded 12 times in a year, this 2.2% interest is going to be compounded continuously, all of the freaking time. So what I don't know is, does that little bit extra here in the 0.05, does that outweigh the continuous compounding? And so we go to the formulas to check. For part A, this is compounded monthly. So our amount for just $1, I just want to calculate it for $1. All I need to know is which is bigger. If I put $1 in, 1 plus 0.0225 divided by the number of compounds in a year is 12. And I'm going to take that to the 12 times 1, or 12th power. In my calculator, I take that to the 12th power. I don't know if you can see that. The glare is so bad right now. I get a 1.0227334, etc. Or one way to think of this is if I put $1 in, I get $1.0227334 out, or a return of approximately 2.273%. For every $1 I put into this account, I get a little bit more, or a little bit less than, well, a little bit more than 2.25 cents extra. Do you understand this idea of the return? Yay or nay, guys? Yeah? Okay. This is also known as your APY, or your annual percent yield. For part B, we're compounding continually. So my amount on that same $1 times e to the return rate, 0.022 for 1 year. That's just going to be e to the 0.022, which is 1.0222438-ish. Which is a return of about 2.224%. So which is the better deal? Yeah. Yeah. The first one does work out in this particular problem, a 2.227 versus a 2.224. And while if it's just $1, that won't make much of a difference. And if it's $100, it won't make much of a difference. But if it's $1 million, it could make a significant difference. The larger your investment is, the bigger difference that will make. Right? Questions on that one? Okay. All right. Okay. Then let's try radioactive decay. All right. So we're going to have a radioactive substance. Decays in such a way that the amount of material remaining after T days is given by M of T is equal to 13 e to the negative 0.015 t, where M of T is kilograms and T is find the mass of this material at T, whoops, it should just be a 0, at T equals 0. And then how much remains? After 45 days. All right. My experience with this has told me that oftentimes y'all overthink these. Try not to overthink these. We're not at a point where we're doing much in terms of manipulation with these functions. That will come a little bit later in the section. We're just trying to get you used to them at this point. So most of these word problems and applications are quite a bit of plug the correct numbers into the correct place in your formula. So When they give you the formula and they ask you to find the mass at t equals 0, they are literally asking you to find m of 0, where t is equal to 0. So m of 0 would be 13 times e to the negative 0.015 times 0. This is just going to be 13e to the 0. And what do we know about e to the 0? Well, this is just 13. And we know that our m of t is in kilograms. So this is just 13 kilograms. How much remains after 45 days? They are telling us here that our t is equal to 45. So we are finding m of 45, which would be 13 times e to the negative 0.015 times 45, or 13e to the negative 0.675. Which when I plug into my calculator, I get 25.53. Did I do that right? 15 times 45, 675. Oh, I forgot the negative of that. 13e negative 0.675. There we go, 6.619. Now, I knew, did y'all see me? I got an answer of 25 and went, oh no, that's not right. I knew that. Do you know why I knew that couldn't be right? Yeah, if I'm starting with 13 and it decays or goes away, then after 45 days, there should be less. 25 is not less than 13. So I knew I had done something wrong. And because I know myself, I knew I had probably forgotten a negative when I typed it into the calculator. And that's exactly what had happened. Okay. Questions for me? Shana, you doing all right? Okay. All right. Let's see here. I'm gonna got that one okay. Let's stop sharing that guy. Should be back to here. Yeah. Okay. So, what I want to make sure we're. Oh. Okay. What I want to make sure we're clear on at this point is that tomorrow is not a standard lecture. Tomorrow is a Q&A session, meaning I will take questions on the homework from 4.1 and 4.2. So if you haven't had a chance to look at either of those, you're going to want to at least look them over and preferably come to class with questions. 4.1 is technically due tonight. 4.2 is due Friday at 11:59. Okay. Anything else for me? All right. Okay. Y'all know about the YouTube channel too, right? All right. It's a sad little YouTube channel, but it's there. You need it. Okay. All right. So y'all take care of yourself, and we'll see you tomorrow with questions. All right. Have a good night.